Hi, everybody. I don't know how many people will be watching this video. I hope not too many because I'm actually having class. This is the first class of fall 2021, Chem 405, and I'm recording this on September 7th instead of our first day, September 8th. And the reason I'm doing this is because I never recorded my first lecture from 2020. I have most of my lectures saved, videos of them from 2020, in case people miss classes for one reason or another this semester, but I didn't ever tape the first one. So I'm going to do that for this first lecture. And so, I'm doing that because people might get sick. I don't want you to come to school if you're sick. You're not allowed to come up to school if you're sick. I might get sick. And somebody might have to quarantine. And also there might be people with health services holds that haven't gotten resolved. So if it's like the first 2 weeks, you could still be a student. You're not going to be taken off the roster until 2 weeks. And so I want to have some way for you to watch the lectures. So anyway, so I have the syllabuses posted, and everything I will be using will be posted on Blackboard. That's the way I run things. And so the handouts for today were the syllabus, the calculus quote review. It's not really review, it's sort of a different point of view on calculus or aspects of calculus, and also calculus problems. I'm not sure how much of that we get to today, but I did give those out. Also, there's an academic honesty statement that I'd like you to do what it asks on there, to read it and to do whatever it says. I think it's to send me an email. Anyway, so I'm going to jump right in. I use OneNote and I share my screen. That's how I run PChem generally. And just to make sure, yes, I'm definitely recording. So, yeah, the reason I'm not just recording the lecture in class is because I just think that might not work for some technical reasons, and I don't want to have it mess me up. So I'm just going to do this at home the day before. So anyway, I'm going to jump right into the subject at hand, which is PChem 1. And I'm going to kind of talk a little bit about where this course is going in terms of like the culmination of the course, because PChem is a place where you actually learn a lot of things. You actually learn in more detail, like where a lot of things that you learned in thermochemistry from like Chem 104, second semester Gen Chem, you kind of learn where they come from in this course. And so I call it sort of previews of coming attractions, because we don't actually start with what we're going to end up with. We don't start with the culmination of the course. We have to work our way there. So this is going to be kind of an intro, and then I'll have to start from the beginning with when I start with the material in successive order, the order that it should go. So right now this is kind of, like I said, this is like previews of coming attractions. None of us, or probably none of us, have been to the movies much in the last year and a half, but I always used to like to watch the previews. So I hope that you do too. So this is sort of an introduction to the class and why it's so cool, because it really is cool. PChem is cool. So anyway, we studied thermodynamics mainly in this course. And thermodynamics is the study of energy and energy flow in what we call macroscopic systems. What do I mean by macroscopic? If I was in class, I'd ask and maybe get a response, but since there's no one here, I'll have to tell you. Macroscopic means a large collections of particles or molecules. Don't have to be molecules, but and what I'm talking about is I'm not talking about 10 or 100 or even 10,000. I'm really talking about on the order of like Avogadro's number. Also 10 to the 23rd, or maybe 10 to the 20th, that would be fine too, or even 10 to the 18th, but certainly not any kind of handleable number, like 100 or something like that. And of course, you know, this type of system that we're interested in is, well, we're chemists, right? So the systems that we're interested in are chemical systems. And obviously that'll be our focus. And what we want to do is we want to understand and also be able to make predictions about chemical reactions. And what we focus on really is chemical equilibria. So that's where the focus is in this course. Okay, so let's see. So chemical equilibrium. Well, you know, from general chemistry, you have seen what chemical equilibrium, you know, we're talking about, like, say, A plus B goes to C plus D, you know, reactants goes to products, where we have a double arrow. So this reaction could go both ways. To make it a little more realistic, you would have stoichiometric coefficients that were not 1. So sometimes we would represent the reaction like this. And that's what we'll do, you know, later in the course when we actually get to this. But what I want to talk about now is what exactly about this equilibrium, what exactly does thermodynamics help us answer? So there are some questions that I'm going to focus on. And the questions are, you know, will substances react spontaneously? That's making a prediction. They'll react, they won't react, that sort of thing. So that's sort of, I'll call that question 1. Question 2 would be something like, you know, how far does the reaction go? Another way of saying that would be like, where does the equilibrium lie? And what I mean by that is, you know, well, what are the product and reactant concentrations at equilibrium? That answers that question. And the third question is, how will that equilibrium respond to changes in conditions? And the conditions that we will be talking about are temperature, pressure, but most importantly, from a chemist's point of view, is moles of reactants, moles of products. Okay, so how will the equilibrium respond to changes in conditions? It's conditions, pressure, temperature, moles of A, B, C, or D, reactants and products, okay? So answering these 3 questions, for just about any reaction, you can write down that there's data for. I'm going to have to use some, well, I don't want to get ahead of myself, but for many reactions, answering this question is like the culmination of this course. And their answers, the answers to these questions, come from the laws of thermodynamics. And the most important of these is the second law of thermodynamics. And so I'm going to just sort of, like I said, give you this introduction. And I'm going to use for today, this is today's reaction that I'm using sort of as an example, is the reaction between ammonium thiocyanate. Sorry, wait a minute. Oh, I guess I used ammonium chloride last year because I actually make this up. And barium hydroxide. These are 2 solids reacting to produce barium chloride, which is also a hydrate, and that forms at an aqueous form, 2 ammonia molecules and 8 water molecules. Okay, so this is the reaction that I'm focusing on. So let's talk about question 1. And if you remember, question 1 was, will this reaction go? Okay. And I guess to be more specific, will it go forward spontaneously? And this word spontaneously means on its own. Okay. So in thermodynamics, the question of spontaneity is governed by the second law of thermodynamics. So spontaneity gives rise to talking about the second law of thermodynamics. All right. So I'm going to give you the second law. This is a statement of the second law. And the statement is total entropy. Sometimes that's called the entropy of the universe. But I'm just going to say total entropy increases for a spontaneous process. That is to say that if something happens spontaneously, the total entropy must have increased. The total entropy must increase for something that happens on its own. Okay, I haven't really defined my terms here. I haven't talked about what entropy is. So do you remember anything about entropy? If you think back to Chem 104, I've had some of you in this class in Chem 104, we talked extensively about entropy, but it was the end of the semester, so do the best you can. If you reach back in your mind to what entropy is, you will think of the word disorder. And this is really a very good way to think about entropy. Okay. So when you look at this reaction, here's the reaction again, right here. If you look at this reaction and what I'd like you to do is to ask yourself the question, does entropy increase or decrease for this reaction? Okay, so you've got these two solids, which are rather complex structures coming together, giving you an aqueous compound, a couple of simple gas molecules and simple liquid molecules. Okay, so if you've had a little while to think about this, I hope that you would remember from Gen Chem that this reaction has more moles of gas on the right side. That's the product side, right? Than it did on the reactant side. So that's one reason why you would think that the disorder or entropy increases in the reaction. That's one reason why. Another reason is that you're forming gases and liquids from solids, but it's not like you're taking the same substance and you're doing a phase change to it. If you did that, then that rule of thumb is the entropy change would be positive. These are different substances, but in general, gases have higher entropies than solids, things like that. And another very important thing to notice is that you formed a greater number of sort of simple, sort of less complex structures from more ordered and more complex ones. So, you've taken these crystals and reacted them together, and you've got lots of simple gas molecules and water molecules and things like that. So all of these things would tell us that the that the entropy for this reaction, the entropy increases. So we say the entropy increases, okay? It increases. But does this tell us everything to know that we need to know in terms of figuring out if this reaction is spontaneous or not? And if you go back and you look at the second law that I've just written over here, it says total entropy increases for a spontaneous process. So when we've considered entropy just now, we have only considered the entropy of this reaction. We've only considered the entropy of the reactants and the products, okay? We have not considered at all, we don't know, what do I mean by total entropy, okay? So what we've done is we've considered, this leads to the entropy change to what we call the system, okay? And in thermodynamics, we have a system and we have the surroundings. All right, seems like it is now recording. I don't know what you missed. Okay, so I don't know if I'm saying this twice, but the system is the reacting chemicals, the surroundings is everything else, but we only really care about the close friends of the system, the atmosphere, the flask, the flame if there is one, the solvent, things like that. And the total change in entropy, which is the predictor of whether something will be spontaneous, if that's positive, is the sum of the two contributions here, the change in entropy to the system, which for our reaction that I've told you about, this reaction here, we know that that is positive, that's the delta S, and the delta S SIR. And I took away the system subscript because I didn't need it. Whenever we talk about the system, we don't use a subscript. So if you don't see a subscript, you know that I'm referring to the system. Okay, so another quantity that chemists use to talk about spontaneity and predict whether a reaction is spontaneous or not is the Gibbs free energy, the change in Gibbs free energy. And I know that this is something that's covered pretty quickly at the end of Chemistry 104. And so, we're going to spend a lot of time on it this semester. But what you learn in Chem 104 or wherever you took second semester Gen Chem is that if delta G is negative, that correlates with spontaneity. So at the negative delta G, a reaction is spontaneous. So chemists think about things this way. So delta G is kind of the star of the last couple of weeks, 3 weeks or so. I don't remember exactly of chem of this course, but you have heard about it before. And even in biochem, if you've taken biochem, you would have heard about it. Okay, so here is an alternate statement of the second law. And of course, it has to do with the Gibbs free energy. So for a process to be spontaneous, the Gibbs free energy must decrease. What that means is that the final Gibbs free energy after something happens must be smaller than the initial, okay, in order for the reaction to be spontaneous. So that's how the change in Gibbs free energy is negative. Okay, so I'm almost ready to show you this reaction. Where the heck did my link go? Well, it doesn't matter. Let me see if I can get it on YouTube. Let me stop this share. Go back to Zoom. Wait, first let me Here it is. Back to the beginning. Okay. Do another share. And here it is. So I'm going to show you this reaction. Some of it. Oh, let's just play it. I hope you can.
In here we've got some barium hydroxide and ammonium chloride, both solids, you can see. I have a watch glass with some water on it, a temperature probe, and we're going to react them together and see what happens. So I'm going to put that on top of the water just so we can see the effect and mix them together.
So these are the two solids.
At this point,
she's throwing them together. I love the fact that she spills
the probe on.
There you go. Good job.
Okay, now we've got two solids reacting together here, and all I'm going to do is mix them together. Okay, and almost instantly you can see that their state is changing slightly. If you want to go inside it, you can.
Two solids together.
They're almost clumping together and making almost like a paste. Just break down some of these lumps.
Really changing a lot.
And if you look at the temperature,
I'm going to do this reaction.
We've already gone below zero. So this is an endothermic reaction where the products will have more energy than the reactants because they're taking in the energy from the outside surroundings. So you can see now we've actually got quite a pasty liquid, and we've also got quite a big smell going on, and that's because
it's smelling like ammonia.
We have made ammonia.
So you can see it turn the litmus paper.
Now sometimes this goes over 30 degrees, so we can aim for that. But as you can see now, it's completely liquid. So I've got some lumps in there, and it's very cold to the point that I can now pick up the watch glass because the water has frozen.
Oh yeah, she put a couple of drops of water underneath that beaker, and it froze in the watch glass.
That'll probably do if you want to show it in there.
And look at the temperature, it's dropped like a rock. Okay, so I think we've seen enough of this video to know what's happening in this reaction. Okay, hold on. Set up. Let's go back to Zoom, share screen. Okay, so we ran the reaction. And there were several observations. Number one, we saw that a liquid formed. And if you take a look at the reaction, you could easily see that that's the water. There's plenty of water that forms in this reaction. She said there was quite an odor. That's what's caused by the ammonia forming. And in fact, remember, it turned the litmus paper blue. So strong ammonia or odor. And so we know it's something basic, so it makes sense that it's ammonia. And also the temperature dropped like a rock. So it gets very cold. So these are the three things that we can observe from this reaction. Okay, so let's think, did this reaction go? Was it spontaneous? And yes, it did. It was spontaneous. So we know that right away. Really goes, there's lots of liquid forming, there's a very strong odor, so lots of water forms and lots of ammonia, and it gets very cold, something's definitely happening. So we could say that the delta G of the reaction is negative because the reaction is spontaneous, the free energy must be going down. And so the change in the Gibbs free energy is negative. We also could say that the change in total entropy is positive because both of these go with spontaneous. And reaction was spontaneous. So we are able to make these conclusions based on that. But let's see what else we can get from this. So I guess I want to say, but what other thermodynamic information can we get by observing this reaction? Okay. And I want to focus on the fact that the temperature dropped, that the reaction got very cold. Okay, so when a reaction gets cold, what does that tell us? So the reaction getting cold tells us something about the change in enthalpy, right? It tells us that the reaction is endothermic, that it takes in heat. And where does it take the heat from? It takes it from the surroundings. So if we have our reaction in a flask here, and here's the reacting chemicals, and I use my red arrow here to represent heat, and Q is the symbol we generally use for heat in this class, okay? That heat is going into the reaction. Here we have the surroundings out here, and then we have our system here, okay? So we could represent this sort of as a box representing the system, and the heat flows into the system away from the surroundings. Okay. And that's why it becomes cold. You know, that's why when you stand outside the shower and you're covered with water and you really feel cold, it's because the water is evaporating, which is an endothermic process that's taking the heat away from your body. Okay, so let's try to stretch your memory a little bit. And let's ask ourselves to remember, how is delta G related to delta H, right? Delta H is really the heat that flows, okay? So delta G, we learn in Chem 104, is delta H minus T delta S, okay? So note, by the way, there are no subscripts. These are all system properties that we're talking about. So we don't put any subscripts here. And now let's try to analyze the signs. Okay. So what do we know? What do we know about this reaction? We know that it happened spontaneously. So we know that the delta G is going to be negative for the reaction. We also know that the delta S is positive. How do we know that? We know that because, remember, we looked at the number of moles of gas, the fact that we were going from a more complex to less complex particles. And so we have an increase in disorder in the reaction. So you could, I would like to know, what is the sign? Oh, and delta H, but so that makes this term negative. But the delta H, this is an endothermic reaction. So this is positive. So what we see here is that delta S is positive. So minus T delta S is negative, and the delta H is positive. And these are the two terms that contribute to the change in the Gibbs free energy, and they are competing. In other words, they are not the same sign, right? Okay, so we have two competing terms here, and in this case, let's see, hold on. In this case, since we know that the overall, the delta G is negative, we know that the negative T delta S term is the dominant term. Because delta G is negative. Okay, so so we have a situation here, okay, where we have a delta H that's positive and a delta S that's positive. That's our situation here, but we can also have other situations which you've studied also in general chem. You can have a delta H that's positive and a delta S that's negative. Or you can have a delta H that's negative and a delta S that's positive. And you can also have that situation. Okay, so all of these things are possible, and they are all going to be what determines whether the reaction is spontaneous or not. So what determines the sign of delta S? We talked about this. It's whether the order, or whether disorder, I guess I could say, increases or decreases in the reaction. So it's really the reacting chemicals, whether they become more ordered or more disordered. So what determines the sign of delta H? Does anybody know? There's nobody there. So delta H, you know, the biggest contribution to the change in enthalpy of reactions is the bonds that break and the bonds that form. So breaking bonds requires energy. If you're in my class, we do learn this. Breaking bonds requires energy. Forming bonds gets you to a more stable situation, and so it releases energy. Okay, so if you have a reaction, like our reaction requires energy, so it must be that more or stronger bonds are broken than are formed. This will lead to a positive delta H. But there's more energy required than released, so overall the delta H is positive. If you have the opposite situation, then the delta H will be negative. If you form more and or stronger bonds than what are broken. Okay, so this is nice because, you know, we know in our case, we know the sign of delta H, we know the sign of delta S, so we know that the reaction is more disordered. It becomes quite a bit more disordered, and the dominant term is actually the negative T delta S term here that determines the sign of the delta G to be negative, because that term minus T delta S is negative. And the reaction is endothermic, which is because more energy is required to break the bonds and to form new bonds. That's what generally is the case if delta H is positive. Okay, so that's nice. We can analyze why the delta G has the sign that it has. And okay, so that's, so what I'd like to do though is to segue a little bit from delta G sort of back to delta S total, because that's where the second law is directly related, right, to the delta S total. I haven't told you why delta G being negative goes along with delta S total being positive, but we do talk about that a lot this semester. And I'll talk a little bit more about it later. But let's consider, like, remember we did the delta G is delta H minus T delta S. Let's take delta S total equaling delta S plus delta S surroundings. And let's try to analyze the signs for this, for our particular reaction. So for this reaction, we know that the reaction is spontaneous. So we know that the delta S total is positive, that entropy, total entropy, increases. We also know by looking at particles, the fact that so many simple molecules form in this reaction, and you have more moles of gas, we know that the sign of delta S is positive. What about the sign of the delta S surroundings? That's what I'd like to think about. So where can we get information about that? So how can we get some info on the sign of delta S surroundings? And we can do that by thinking about the heat in this reaction. So here's our flask. Here's our reacting chemicals. And we know that the heat went into this reaction because it's endothermic. And of course, we know that there is the surroundings out here, and then we have our system in here. Okay, so heat flowed away from the surroundings into the system. That's characteristic of an endothermic reaction. And in fact, if you looked at the demo that was done very quickly, we started with a few drops of water. She actually put a few drops of water underneath, and it froze. Okay, so that tells us something about what happened in the surroundings. So we had the freezing of water in the surroundings. And that really just makes it very obvious that the entropy of the surroundings decreases because frozen water has more order or less disorder than liquid water. Okay, so the entropy of the surroundings decreases. So delta S surroundings is negative. Okay. All right, so because the heat was taken from the surroundings into the system, the surroundings cools. Whether or not water was able to freeze in the surroundings, the temperature of the surroundings would definitely go down when this is done. And when you lower the temperature, you decrease the disorder. You decrease the amount of motion. You start out with a lot of motion in molecules, and as it cools down, the motion gets less and less. So as the temperature goes down, generally, you're going to decrease the disorder. So in this reaction, and our reaction, I guess I would say that the delta H is positive. So the delta S surroundings is negative. And I guess I would say that removing heat from the surroundings increases order in the surroundings or decreases disorder in the surroundings, which is why delta S surroundings is negative. Okay, so we can get that. Now, let's take a look at our sum, because delta S total is how we figure out if a reaction is spontaneous or not. Now we know that the sign of delta S total is positive because the reaction is spontaneous. So it's the sum of these two contributions. We already know that the delta S is positive because disorder increased in the system. We've just deduced that the delta S surroundings is negative. So now what you see here is that we have, again, two competing terms that have to be thought about in order to determine if the reaction is spontaneous or not. Now, this reaction we know is spontaneous. And the reason for it, if you look at these two different contributions here, we know that the delta S must be the dominant term. that that delta S, magnitude of delta S must be greater than the magnitude of delta S surroundings. Okay. So it's not a coincidence. If you remember when I talked about delta G as delta H minus T delta S, we also had two competing terms, and it's not a coincidence at all. So it's really no coincidence that we got this, these two competing terms, and I'm going to show you why. So this is an equation that we used in general chemistry. We'll learn a lot more about this semester, but you actually will have to use this equation in some of the labs before we get to it in class. So this is a good part of the good review. I'm also going to give a lab lecture on that, lab lecture 3. But what I want to show you is what happens if we divide both sides of this equation by negative temperature. So what you can see here is that this whole thing just becomes delta S, right? The negative T's cancel. This is negative delta H over T. And this is negative delta G over T. But we have another equation, which is delta S total equals delta S surroundings plus delta S. So here's the same delta S here. So what this tells us is that the delta S total equals the negative of the delta G over the temperature, and that the delta S surroundings is the negative of the delta H over the temperature. Okay, and this is something I know that if you had me for second semester Gen Chem, I have students calculate this so that they can add up the two contributions and figure out if a reaction is spontaneously based on the sign of delta S total. It's positive, it's spontaneous, and if it's negative, then it's not going to happen spontaneously. Okay, so I've sort of answered the first question. Will a reaction be spontaneous? And I'm going to go on to question number 2. Now, question 2 basically has to do with how far does the reaction go? Okay. Well, okay, let's start with this. Let's start with the fact that we know that the Gibbs free energy has to decrease if a reaction is going forward. So for spontaneity. So let me rephrase that. If a reaction is going forward, that means it's happening spontaneously, right? Let's say it's happening by itself. Then we know that the Gibbs free energy has to be negative, because for something to be spontaneous, the G has to decrease. So if I were to draw some kind of sort of plot of the Gibbs free energy as the reaction goes on, and in chemistry, we have a word for as the reaction goes on. We call it the extent of reaction, and we give it the symbol X. And it's actually defined, and I'm not going to do it now, but you could basically say that if you're going from reactants, all reactants, to all products, that when you have all reactants, the extent of reaction is 0. When you have all products, the extent of reaction is 1. So that's basically the parameter that it is. But don't worry too much about that. What I want you to think about is that, let's say we started over here. So this is our Gibbs free energy of the reactants. If the reaction is going forward, so as the reaction goes forward, G must drop. So we have a drop in G, drop in G, drop in G. Okay, the reaction goes forward. But what happens at some point? What happens is that G stops dropping. All right, So at some point, the slope here we have a nice negative slope. And here, the slope equals 0. That slope is the change in Gibbs free energy with respect to the extent of reaction. With respect to the extent of react. It is a derivative, dg dx. Okay, so right here, what is this point here? Why? Yeah, Gibbs free energy stops decreasing. Okay. dg dx is equal to 0 at some point. What do you think we call that point? That point is equilibrium. Now, why does it stop there? Well, if it were to go any further, it would go up. Okay. And so it can't go up because that won't happen spontaneously. But what it does tell you is if you started with all products, that the reaction would go in reverse. And in doing so, it would decrease the Gibbs free energy until equilibrium. Okay. And then it would have to stop, the products would have to stop decreasing, because to continue to decrease products would be increasing the Gibbs free energy. Okay, so that there's a dip in the Gibbs free energy curve as you change the quantities of reactants and products. And so that just gives you kind of a general thing. Now, this equilibrium, the reaction doesn't stop dead at equilibrium. This is a dynamic equilibrium. And what that means is that both of the reactions, the forward and the reverse reaction, are still happening. But what happens is that their rates equalize. Okay, so if you remember back to Gen Chem, okay, if you have a reaction, reactants goes to products, what is the rate? Here's an equilibrium. So we have, well, the rate of the forward reaction and the rate constant. So we basically have these two things happening at once. Reactants forming products with a rate constant Kf, and products forming reactants with a rate constant K reverse. Okay, so the rate of the forward reaction, that rate forward, equals the forward reaction rate constant times the concentration of reactants. Because these are elementary, let's say, and so the rate law is determined by what are the reactants, and there's only the one reactant, R, let's say. So the rate of the reverse reaction would be the rate constant times the concentration of product. Now, what happens at equilibrium? Okay, well, what happens, like I said, is that these rates become equal. So that means that I can equate the rate forward with the rate of the reverse. So that means that Kf times R equals Kr times P. And if I just rearrange this a little bit, I end up with the concentration of products over the concentration of reactants is the K forward over the K reverse. But these are rate constants. these don't change unless the temperature changes. So these are constant, which tells you that the ratio of the concentration of product over reactants is constant. And we call this the equilibrium constant. Okay, so it's that point in the reaction where going forward would increase the Gibbs free energy, and that we call the equilibrium point. And at that point, you basically have equal rates of both things happening, and that ratio is the equilibrium constant. Okay, lots to swallow, but I just want to refresh your memory. I want you to recall that there is a very simple, definite relationship between delta G. Now I'm going to put the little 0 here. That means under standard conditions, the change in the Gibbs free energy is minus RT times the natural log of the equilibrium constant. And that's that funny ratio of products to their stoichiometric coefficients over reactants to their stoichiometric coefficients. We will derive this at the end of Chem, and it's like basically a very important relationship. This is the temperature, this is the gas constant, and it would have to be in joule units. And so you could see here that if the K equilibrium is less than 1, right, that favors the reactants, a very small value. The log of a number less than 1 will be negative, okay? And so delta G0 will be positive. So favoring the reactants goes along with a positive delta G0, okay? If, on the other hand, K is greater than 1, which favors the products, then minus RT log of K, the log of a number greater than 1 is positive, and this negative sign will make the delta G0 will be negative. So a negative delta G goes along with favoring the products and a large value of K. So this relationship definitely makes sense. All right, so that's the first 2 questions. And now I'm left with question 3. And question 3 is, how is equilibrium affected by conditions? Temperature, pressure, moles of reactants and products. Okay, I'm just going to talk a little bit about how it depends on temperature. Okay, and I'm really doing this to make a point, which I'll talk about at the end. All right, so we know that the equilibrium constant depends on delta G from that equation I just gave you, okay? And in order to know how the equilibrium is affected by changing these conditions, we need to know how is delta G affected by these changes. Okay, so let's consider like a reaction, like our reaction that I've been talking about, which has a negative delta G. So suppose we have a graph here, and this is the Gibbs free energy. And here's our Gibbs free energy of the reactants, and here's the Gibbs free energy of the products. And this is showing a negative delta G of the reaction. Okay, and I know that because this is going downhill. Delta G reaction is negative. Okay, it goes downhill. And this is at some temperature. So let's suppose that as the temperature increases, suppose that if I increase the temperature, that now the delta G is different, okay? And I'm going to draw a new diagram. So let's say here's my reactants. And now my products are down here. And look, I'm drawing them a lot further down. So I'm really exaggerating this. Okay, so this is delta G0 reaction at the higher temperature. Okay, so what I want to know is how would this scenario, if this is the scenario for our reaction, how would this affect, how would this affect the equilibrium? In other words, would the products or the reactants be more favored or less favored at the higher temperature? Okay, so you can see here that you have a larger negative, a more negative delta G0 at the higher temperature. So what is that going to mean? Well, it means that whatever your K was here, this K is going to favor the products more. So I guess I'm going to write that the products would be more favored at the higher temperature. Okay. So it seems kind of logical that in order for us to deduce how the equilibrium constant changes with temperature, we really need to know how the delta G changes with temperature. Okay. And so we'd have to think about something like a derivative, the change in the delta G of the reaction with respect to temperature. Okay, so, well, I can actually sort of fast forward and tell you that this is roughly, this change in the Gibbs free energy with respect to T is roughly proportional to the negative of the delta H of the reaction. Okay, so that actually tells us that this change in the equilibrium constant, how it changes as the temperature goes up or as the temperature goes down, that this differs depending on whether the reaction is exothermic or endothermic. So, like, how is this helpful? Let me show you how this is helpful. It allows us to figure out how the delta G, how the Gibbs free energy changes with temperature. Now, I'm going to show you this graphically, but I don't know the graph for how delta G changes with temperature. Only thing I know is how that delta G changes is roughly proportional to the negative of the delta H. So if delta H is positive, then this derivative is negative. So what I'm going to do is I'm going to shut my eyes and just going to draw a graph, just going to draw a line going down or something squiggle going down, representing how the delta G0 changes with temperature. So what does this mean? Like, delta H is positive. We know that the derivative will be negative because it's proportional to the negative of the delta H. So the slope is negative. So that means as the temperature goes up, the delta G0 goes down, right? It's heading downward. It's got a negative slope there, okay? So as the temperature goes up, and even if you didn't know what the value of delta G was, you know that delta G0 will get smaller. Okay, that means less. So if it's positive, the number would be smaller. If it's negative, the number will be bigger. okay? And in our reaction, in the demo reaction, delta G0 was negative. So as the temperature goes up, it gets more negative. So what does this predict in terms of what would be favored more? Okay, so that means at a higher temperature, products will be favored more. Okay, so this is all new and not too well explained because I'm trying to give you a preview, so don't worry if you don't understand everything today. But I want to talk about how does this sort of jive with general chemistry ideas. Okay, and in general chemistry, we use Le Chatelier's principle when we talk about changing things, like putting a stress, increasing the temperature is a stress, for example. So what would Le Chatelier's principle say? Well, remember, Le Chatelier's principle says a system responds to an applied stress, which is like a change in conditions, aka a change in conditions, by acting in such a way as to reduce or relieve that stress. Okay, so that's Le Chatelier's principle. So we have an endothermic reaction. That means this is the one I demoed, okay? That means reactants, we could put the heat on the reactant side. That's typical of an endothermic reaction. So what happens if we add heat? That's the stress. It's like we are adding heat. What that does is the reaction has, the only thing it can do is take away that heat. That drives the reaction forward. Okay. And at the new temperature, you would end up with products being favored more. So you would have a greater value of the equilibrium constant. Okay. So we just concluded the same thing. If you remember when I talked about this derivative here, since the delta H is positive, the slope of delta G versus T is negative. As T goes up, the delta G0 goes down. The products will be favored more. Okay. That's what we got from our analysis using basically the Gibbs free energy. And you would get the same answer from Le Chatelier's principle because it's really based on thermodynamics. Okay, so one reason I'm telling you this is a preview of coming attractions. Another one is that it tells us that this quantity, the derivative of delta G, the change in delta G with respect to temperature, is important. Okay, it allowed us to make this conclusion. All right, and so this is an appropriate segue into sort of talking about multivariable, about PChem, which involves functions that have sometimes more than one variable. So the change, the derivative of the delta G with respect to T, this comes from the derivative of G with respect to T. Okay, but this G here, this Gibbs free energy, doesn't just depend on temperature. G is what we call a multi-variable function. It depends on many things: temperature, pressure, and moles of all the reactants and the products. Okay, so in this case, we would say G is G of, we just have R goes to P, one reactant and one product. We would say temperature, pressure, moles of reactants, moles of product. Okay, so that would be a function that depends on 4 variables. Okay, so when we talk about how the Gibbs free energy changes with temperature, we can't even call that a derivative anymore. We have to call it a partial derivative. A partial derivative of G with respect to T. And so we say dG dt, or partial G partial T, are all ways of saying this. Okay, and in P-Chem we deal with functions of more than one variable, you know, all the time. I think I'm pretty much done for today. But I'll start with this next time, which will be Monday, September 13th, and then we'll have a lab lecture after that. So, okay, I'm gonna stop this.